For this video, we are going to verify the given pairs of lambda values and vectors if they are eigenvalues and eigenvectors for the given 3 by 3 matrix. Our 3 by 3 matrix here, matrix A, we have the entries negative 2, 2, and negative 3, 2, 1, negative 6, negative 1, negative 2, and 0. To verify or to show that the given pair, when you say pair, this pair of lambda value and we have here vector x, same thing here, same thing here. We are going to show that these pairs are eigenvalues and eigenvectors of matrix A. To do that, we need to show the concept of multiplying our matrix with a certain vector depending on which pair we're going to refer must be or can be represented by the product of the corresponding lambda value times the same vector. If we can do that, then we have already shown that the pair of lambda values and vectors are eigenvalues and eigenvectors of matrix A. So let's start with the first pair. So this would be the first vector must be equal to the product of your lambda sub 1 and your same vector. So our A here is negative 2, 2, negative 3. We have 2, 1, negative 6, negative 1, negative 2, and 0. To be multiplied with our first vector, x sub 1, you have 1, 2, negative 1. If the result of this later can be represented as the product of your lambda sub 1 and your first the same vector, then we can show or we have verified that lambda sub 1 and is the eigenvalue with the corresponding x sub 1, the eigenvector of matrix A. So we have here the product. Take note that we are multiplying a 3 by 3 matrix by a 3 by 1. So we are expected to have a result which is a 3 by 1. Please don't forget to use the proper operations when multiplying matrices. Let's do it step by step. Negative 2 times 1 is negative 2. 2 times 2 is 4. So negative 2 plus 4 is positive 2. We have here negative 3 times negative 1 is positive 3. So that's positive 2 times positive 3. Plus positive 3. So you have positive 5. Again, negative 2 times 1 is negative 2. Positive 4. Positive 3, that's positive 5. That's correct. Next, 2 times 1 is 2. 1 times 2 is 2. So 2 plus 2 is 4. Negative 6 times negative 1 is positive 6. 4 plus 6, you have 10. Next, negative 1 times 1 is negative 1. Negative 2 and 2 is negative 4. So negative 1, negative 4, that's negative 5 already. 0 times negative 1 is just 0, so this is negative 5. Once we're done doing that, let's focus on our lambda. That's 5. So let's take out that 5 here and see if this matrix here is the same vector here, or matrix vector in the form of a matrix. When we take out 5, that's 1. 10 becomes 2. Negative 5 becomes negative 1. As you can see, this is our first lambda, and this corresponds to our first vector. This means that we have verified the pair of lambda 1, which is 5, and x sub 1, our vector, which is a vector of 1, 2, and negative 1, are eigenvalues and eigenvectors, respectively, of the 3 by 3 matrix. Second pair. So we need to show this. Sorry, that's 2. Okay. So A times your second vector. A is the same thing. Negative 2, 2, negative 3. Next, you have 2, 1, negative 6, negative 1, negative 2, 0. To be multiplied with your second vector, you have here negative 2, 1, and 0. Again, the result should be a product of your lambda sub 2 and the same vector here. So the same thing, 3 by 1 will be the result. multiplying a 3 by 3 by 3 by 1 matrix. So you have negative 2 times negative 2 is positive 4. 2 times 1 is 2. Sorry, 4 plus 2 is 6. This is 0. So we have here 6. Next, 2 times negative 2 is negative 4. 1 times 1 is positive 1. Negative 4 plus 1 is negative 3. This is 0. So you have here negative 3. Finally, negative 1 times negative 2 is positive 2. Negative 2 times 1 is negative 2. That's 0. Another 0. So 0 here. Now let's take out our second lambda of negative 3 and see if this matrix will return to negative 2, 1, and 0, our second vector. When we factor out negative 3, the 6 becomes negative 2. The negative 3 becomes 1. And of course, this is 0. This is, again, our second lambda. And this is our second vector. And since we have satisfied this, negative 3 is an eigenvalue of this matrix with its corresponding eigenvector, the vector x sub 2, which is negative 2, 1, and 0. Finally, we have the last pair. So let's do it here. You have A, and then the third vector should be the product of lambda sub 3 and your third vector. Of course, our A is the same. So this is our A here. Negative 2, 2, negative 3, 2, 1, negative 6, negative 1, negative 2, 0. To be multiplied with our third vector, 3, 0, 1. Take note of our lambda, negative 3 as well. So 3, 0, 1. So you have here 3, 0, and 1. So we are going to show that this will also result to this value here, or the result of this lambda sub 3 times your third vector x sub 3. So let's try to multiply this step by step. You will have a 3 by 1 result. So negative 2 times 3 is negative 6. That's 0. Negative 3. Negative 6. Negative 3. So you have negative 9. 2 times 3 is 6. That's 0. This is negative 6. 6 plus 6, 0. Let's make 0 better. Alright. Negative 1 times 3 is negative 3. This is 0. That's 0 as well. Negative 3. So the result is negative 9, 0, and negative 3. Our lambda sub 3 is negative 3. So when you are going to factor out negative 3, this is positive 3. That's 0. That's positive 1. This is our lambda sub 3. And of course, 3, 0, 1, looking back here, is our third vector, x sub 3. This means the eigenvalue of negative 3 with its corresponding eigenvector 3, 0, 1 is fit and it's good for the given matrix A in this item. This is how we verify eigenvalues and eigenvectors for a 3 by 3 matrix. Thank you very much for watching.